cut off before. I think it was right before friction, and there certainly was a lot of friction in chapter 5. So it's mostly chapter 5 and chapter 6, right? But chapter 5 had a lot of the friction stuff in it, and we technically didn't have the laws of friction on the last exam. So take a, I put them up before the weekend so that you have a chance to try stuff out and then ask questions next week. So our goal for today is to finish talking about power, and there's just a couple of comments I wanted to make about these work energy relations in particular. Now that we've got a lot of experience or some experience with problem solvings, generic guidelines for how to choose what's in your system. You have a lot of latitude for how to choose your system, but sometimes one decision is better than others. It will either make things easier or it will be impossible if you choose the wrong system. So let's look at that. Here's our, I didn't put the work kinetic energy theorem on here, but here is our latest one that this is only true for conservative forces we now know. You have non-conservative forces that are internal, you just leave that on the left-hand side, but every conservative internal force, we're assuming here that you've put it into a potential energy term on the right-hand side. So how can we get some guidelines for how to choose the system? Well, first of all, if you don't know a potential energy expression, you have no choice to, you really don't want that force to be in the system because you have to know what the potential energy is. So if it's not gravitational or spring, those are the only potential energy formulae we know. So leave it external to the system. Don't make it an internal part of the system. If you have a conservative force and it's not constant, for example, you have a conservative force and it's not constant, you won't know how to calculate the work. The only way we have shown for how to calculate work is if a force is constant, we can calculate Fx delta x. Early on, we did a problem where we had a hemispherical bowl like this, right? And we had a little ice cube that was sliding down to the bottom and it was moving fast down at the bottom. And gravity is certainly doing work on it, but it's moving in different directions, and gravity's pulling it a lot in the direction it's going when it first starts out. And it's hardly pulling it at all in the direction it's going by the bottom. So it's certainly not a constant force, and we can't use Fx delta x to calculate the work done by gravity. So I wouldn't want that gravitational force to appear on the left-hand side, because then I'm going to have to know how to calculate the work. But if it goes on the right-hand side, hey, we know the potential energy. We know y initial, y final is smaller, so mg times delta y could go in the potential energy formula. So that's a case where you want to keep something internal to the system. And then finally, I think this is a little too low here. I got to move things up. There we go. If the force is non-conservative, well, we don't really have a choice of putting it in as a potential energy term. So either you're going to put it over here with a plus sign, or you're welcome to move that over there with a minus sign, but you're going to have to put it into that. It's going to have to be calculated as a work, or at least probably given to you as a work. Or maybe you're given everything else and you're asked to calculate that, and you can solve for that as your unknown. Okay, so those are some guidelines that hopefully make sense. You can't always do any kind of system that you want, but frequently you do have quite a bit of latitude. So again, here are 3 big work energy relations, and now I want to talk about generally the notion of the conservation of energy. The idea with conservation of energy is if you have everything that matters inside your system, or another way of saying that is your system is isolated from all external influences. So no external forces can do work, then that left-hand side in any one of these relations is going to be 0. So if we imagine taking, for example, just this most general one, if we take all the external forces that are no external forces doing work, then the idea is everything's inside the system, and there are lots of changes in energy state of the system. So one could think about not only changes in kinetic energy. Kinetic energy means large chunks of mass either speed up or slow down, right? Those would be positive or negative changes in potential energy, of kinetic energy. Potential energy changes means springs, whether invisible forces or actual springs, compress or expand. But, also your system could heat up. And usually, we know, because we've learned about molecular dynamics or molecular motion early on in our science career, we know thermal energy is really a kind of kinetic energy. It's kinetic energy at the molecular level. But from the point of us here in the laboratory, we usually see it as kind of missing energy, or energy that we don't see with our eyes. You can measure it with a thermometer. So a lot of times people just think of that as a separate thing, even though you could really include that in a kind of change in kinetic energy. Same thing with chemical and nuclear changes. You could think of these as like changes in potential energy. When you have one chemical substance turn into another chemical substance, usually energy is released because it's sort of like some springs were compressed and they get to relax. That's a chemical reaction that wants to spontaneously happen and would be exothermic. And same thing with nuclear. So you can really think of anytime you isolate your system, there's just lots of changes within the energy of the system. We say energy is conserved overall, absolutely. If you take care to keep track of everything, including all the heat that's generated and everything down to the molecular level, energy is always conserved. If you're sloppy and you say, well, I was just looking at moving masses, here was my system and I pushed it, it had a lot of energy to begin with, and then there was none. Well, we would say energy is not conserved, but really what the problem was, I didn't keep track of all the energy at the molecular motion. I heated up the table by the friction that was sort of creating some thermal energy at the molecular level. If you keep track of everything, we have the idea of conservation of energy, but it's not always apparent at the level of macroscopic kinds of experiments. Okay, last topic. I wasn't sure if we were going to get to this before the exam cutoff, but we are. And that's why you have that strange two, if you notice, there's an assignment with 2 problems on it, just to give you a little more practice with power. You'll see some power stuff in the exam review stuff that I put on the website as well. But what's the notion of power? Well, when I do work on a system, I could do the same amount of work, but might do it at different rates. For example, if I've got a mass, I might be lifting it up at a really slow rate. Maybe I think of my system as just this block, right? My hand is doing a certain amount of work as I lift it up 1 meter, but it might take a very long period of time if I'm lifting it slowly. Maybe again, I'm lifting it at a constant rate, but I'm lifting it really fast. I'm doing the same amount of work as it moves up 1 meter, assuming I'm moving it at a constant rate, because my hand is exerting the same force. The acceleration is still 0, so my hand force balances out the weight force, and I'm moving it 1 meter. So in that 1 meter of motion, I'm doing the same work, but it takes less time. So the rate at which I'm doing work, that's what power is referring to, is different in this case. So we talk about the power output of a force is the rate at which it's doing work, how fast it's doing work. We're concerned with, it's sort of from our body, we think it's a lot harder to push a heavy box really fast than it is to push it slowly, although the notion of effort isn't exactly aligned with power. The SI unit for power, well, the numerator would be joules, that's work, and the denominator seconds, so joules per second, but it's so common that we use the shortcut unit of watts. So we'll be measuring, for the most part, units of watts. I can't remember I may have eliminated it from the homework, but at one point there was a non-SI unit that appeared, which was horsepower. I don't know if that's the official English unit or if it's just an antiquated unit, but in any case, if you find something that asks for an answer in horsepower, you can compute it in watts and then just Google what it's certainly the conversion factor is in your book as well. Giancoli mentions horsepower, but that's the other common unit for power. But on electronic devices, you're always going to see watts. So now the work that's done by the force that's acting on the object or the system that we're talking about might be doing positive work or negative work. So if there's positive power, that means the external force is doing positive work in a certain amount of time. So it's the rate at which it's doing positive work. If I'm pushing a heavy box along the floor, I'm doing positive work on it. It's translating in that direction and I'm pushing in that direction. That's the hallmark of doing positive work if my system is the box. And energy is being transferred. So I can think of I'm doing positive work over here. I might be changing the kinetic energy of the box, right? If it's on a frictionless floor, it would start accelerating. So that would get more and more kinetic energy. Or maybe I'm changing the potential energy of the box, right? I might be pushing or I guess I wouldn't say the potential energy of the box, the potential energy of the box Earth system. Maybe I'm pushing it up an inclined plane. I'm doing positive work on it as I push it up, but I'm increasing the potential energy stored in the system. Or there might be some non-conservative internal forces, maybe friction between the box and the floor. And I might be heating up the box and the floor as I grind it along the floor like this. But in any case, I'm transferring energy into the system, either speeding up the parts, increasing potential energy, or heating it up, or something like that. It's also possible to transfer negative power to something. And what that means is it's really transferring power to you. That would be the opposite. Maybe for whatever reason, the box is sliding in that direction and I'm trying to hold it back. Maybe it's on an incline, right? The box really wants to slide down the incline and I'm pulling back, but I'm not successful in keeping it back. So I'm pulling in that direction. It's translating in that direction. We would call that negative power. Most of the time, we're talking about positive power that's being transferred to a system, okay? So we're gonna start out the same way we did with velocity. We'll define an average power as an amount of work done divided by delta t, and then we're gonna define instantaneous power. I'm not sure what happened there. That's supposed to be a little bar over the, oh, what's going on there? I've never seen anything like that happen in PowerPoint before. In any case, the bar means average. So average power is just the work that's done divided by the corresponding amount of time it took to do the work, kind of like average velocity, right? So let's do a quick example. I'm not even going to do it on the board. I'm lifting a 3 kilogram block upward at constant speed, and suppose it moves up 0.5 meter in 2 seconds, okay? And the question, the thing I want to answer is, what average power am I delivering to the system block, right? So I'm talking here, there are lots of different systems I could take, but here let's just consider the particle, the block. My hand is delivering an average power to the system, which is the work I do, and that's just force times displacement. My displacement is 0.5 meter, and the force is, well, I'm moving it at constant speed, so my hand force exactly balances out the weight force. So my hand force is mg in this case, okay? And it's doing positive work. I'm pushing up and it's lifting up. So I'm talking about the power delivered by my hand to the system consisting of the block. So my hand force is just mg because it's not accelerating. Here's the distance it moved through. So that's fx delta x. And we divide by the amount of time it took. 7.35 SI units, 7.35 watts. If the system is the block, I'm not the only thing doing work on it as I raise it up at constant speed. Gravity's doing work on it too. It's another force, right? So gravity's doing work on it, and it's actually doing negative work. It's going up and gravity is pulling down, but unsuccessfully keeping it from moving upwards, okay? So it would be, the only difference is there's a negative work in the numerator. And there again, the force is mg, but the force x component, if x is up, the direction of displacement is going to be negative. So gravity is doing negative, delivering negative power to it. And so overall, no power is being delivered to it. And that seems to agree with our work kinetic energy theorem, right? If you do no overall work on something, it shouldn't be speeding up or slowing down. You could also take other systems. For example, we've been talking about systems like block plus Earth, where gravity is an internal force. That's another possible thing. And I could think, well, in that case, gravity is an internal force. The only external force that might be delivering power to the system, consisting of the block plus the Earth, is my external hand coming in. And so my hand is doing positive work on the system, and the power, the rate at which I'm delivering energy to the system is 7.35 watts. But the idea is the system's not gaining kinetic energy, but it is gaining potential energy in that case. So the view is kind of different. Before, when we considered our system to be the block, there was no energy being delivered to it as time went on, and so it wasn't speeding up at all. In the second case, there's overall net work being done on the system, but it's still not speeding up, but it is gaining potential energy because it has two pieces with an invisible spring between them. Okay. Now, our goal is not to talk about average power, but instantaneous power, right? I might lift a book first slowly and then quickly and then slowly or something like that. So the power would be changing, and the faster I'm moving the book, it seems like the faster I'm delivering power. So we want a notion of instantaneous power. And we could just use that definition that we had for the average power, right? I could say if my force is constant, at least for a very small amount of time, the force of my hand might be approximately constant. Excuse me. And so if it's approximately constant, I could approximately use the formula Fx delta x to calculate the work in the numerator. And then I just inspect this delta x over delta t. I'm imagining the instantaneous power is going to be when delta t gets really small, and delta x would get really small. And the limit as delta t gets small of delta x over delta t is our very definition of the velocity. So this is the second formula for power. This one's for instantaneous power. The instantaneous power can be gotten by the force, so x is the direction the object is moving or being displaced. The force you're applying to it, x component, times its velocity, x component, along the direction it's going. So let's do an example, and I've probably been clicking too much, so let's unshare the screen and do it at the board. But let me put it back up for the sake of me. So we've got a 400 kilogram block is pulled at constant speed of 2 meters per second up a frictionless incline 20-degree plane. And our goal is there's a winch, winch that's on a truck that slowly pulls in a cable. So there's a motor up here at the top that is winding in this cable. And the question is, how much power is the winch delivering to the system, block plus Earth, where gravity is an internal force? It's pulling it up at constant speed, so it's not changing its kinetic energy, but it is increasing the potential energy of that system. Okay, well, to calculate that, let's see. It's moving at a constant speed of 2 meters per second. So if I draw a little cartoon over here, kind of draw the same picture, it's a 20-degree incline plane, 400 kilogram block, and there's a little winch that's attached up there, and it's slowly reeling in the cable. And the plane, it says, is frictionless. And so this thing's moving up at a constant speed of 2 meters per second. I think I've got all the pieces that are in the problem there. And the question is, how much power is this winch delivering to the system, block plus Earth, where gravity is internal? The answer would be the same if we just said the system's the block, but for some reason I decided to say that system. Well, we always, the direction something's being displaced, we're in the habit now of calling that the x direction. So I'm going to call x the direction that the block is being pulled up the plane. And we just got the formula. The power is equal to Fx times Vx.
Dr. Kelly.
Yeah.
If we can't see the board, if you're like drawing.
Oh, am I too far over, or am I not showing it?
Yeah, go to like the left a little bit more.
Oh, okay. Sorry about that. I've got my PowerPoint up so I can see the problem, and therefore I don't know exactly where this is aimed, but is that good now?
Yeah, that's good. Thank you.
All right. Thanks for letting me know. Okay. Well, we're talking about the force we're talking about is the tension in that cable, and the speed is given. So we're halfway done, not really halfway done. Maybe I could write it this way. We want the x component of the tension times the velocity x component, which is 2 meters per second. So all we need is the tension x component, and the tension x component is the tension because the tension's all along x, right? So how would we find the tension? We're going back to chapter 4 now. Free body diagram, right? Let's draw down here a little cartoon of this thing tilted. So there's my object of the free body diagram. I've got a 400 times 9.8 going down. I've got a normal force here. It's frictionless, so there's no friction force going back that way as it gets pulled up. But I do have a tension force going there. And I need to put axes on there. Most of the time, in this case, nothing's accelerating. So our heuristic about if you all should always align one of your axes with the direction of the acceleration doesn't tell us anything here. But the motion is along the plane, so it seems to make sense to choose our axes parallel and perpendicular to the plane. I've already taken plus x to be the direction it's going. Let's call plus y perpendicular. And I want to know something about t. So let's just use the x components of fx equals max. Sorry, sum of the force x components equals max. All right. T certainly has an x component, and it's all x, comes in with a plus sign in my coordinate system. This has 0 x component, and this has a negative x component, right? I'm going to draw in my usual angle that many of you are familiar with drawing in when we have things sliding on inclined planes. That angle is also 20 degrees that I've drawn in there. So it looks like to get the x component, it's going to be negative of magnitude 400 times 9.8 times the sine of 20 degrees. The third force has 0 x component, and it's moving at constant speed. So all components of constant velocity. So all components of acceleration are 0. And so our tension is, oh, you guys are calculating it for me. I don't think I have a calculator here, but I get the tension. I plug it in up there. I see what the power is. You guys will tell me in just a second. So once you get that tension, multiply by 2, that's what the instantaneous power is there. Anybody have a number for the tension yet? 1,340 newtons, I'm assuming SI units. So double that, 2,680 watts SI units, right? We put all SI units in, so we know we get the SI unit out. Sounds like a lot. I mean, it's a heavy item that's being pulled out the plane, so I guess not surprising. Yeah. It's negative because we're doing force x components. We chose x to be up the plane, and in going from tail to tip, I'm going more or less in the negative x direction and negative y direction. So the x component's negative. It's pulling back against the direction it's moving. In other words, gravity wants to pull it down. All right, let's go back to screen share. So this is the same solution. We can check it. 2680. All right, good. Here's a different example where the power isn't constant. Power might not be constant, right? And in fact, one of the cases where power isn't constant is when you have an object and gravity keeps speeding it up, right? The weight force of gravity is constant as this falls, but the velocity along that direction is increasing, and that means the power is getting bigger and bigger. Gravity is transferring more and more energy to this thing as time goes on, or at a greater and greater rate, I should say. You know, I'm not going to spend much time on this, but same formula, right? Let's take plus y going down. Fy is mg, and Vy is some function of time, and we know how Vy depends on time. That's our old kinematics stuff, right? Here's Vy equals Vy initial plus Ayt. If we take it to be at rest initially, it's just 9.8 times t. I'm taking plus y to be down, okay? And that means the power is some number times time. So the power is going up linearly with time. Gravity is transferring more power at a greater and greater rate, or doing work at a greater and greater rate as time goes on. Any questions on, I don't have a worksheet to do on power, but that's kind of the two varieties of things, either average power, instantaneous power, and they're pretty easy formulae to use. You just got to find the relevant force, and sometimes you have to use free body diagrams. Okay, on to chapter 7. Again, chapter 7 is not going to be covered on our exam. We just don't have enough time to do the homework on it and all that kind of stuff. But by the time Monday is finished, you know, we may be getting closer to done with chapter 7. Okay, so it has to do with the concept of impulse. Most of you has zero intuition about the word impulse, but most people talk about momentum sometimes, and we'll talk about colliding objects here. So here is a video. You know, actually this lines up well with our talk we had today. Let me click on the video and hope, no. I thought if I click on it, it would play. What do I have to do? No, do I click over here? Is there a keyboard shortcut to play? It worked back in my office. No. It's supposed to show. Well, yeah, usually it doesn't work when you're not in presentation mode. I'm sure there's a trick that I've known before, but actually I tried it in my office in presentation mode and it worked. So something is going different on this. Let me try clicking with this. No. It's a video that shows, well, disappointingly, I'm gonna have to describe it to you because it's amazing. Maybe you've seen videos like this of how much balls. So here's a baseball being fired, probably with a pitching machine or something like that, at a piece of rigid steel over here. And it's just a slow-mo of amazingly how much the baseball compresses. You know, it compresses to about half of its width. So it's a pretty impressive compression. The golf ball, which is on the next one, if you've ever seen that before, the golf ball turns into a complete pancake. I mean, it's probably 1/6 of its original diameter, maybe less, and flattens out into this really wide thing, and then bounces back to its same shape again afterwards. The point being that I just wanted to get you to think about the force that this wall is exerting on the ball as time goes on, right? As the ball is coming in, the force on it, of course, is 0, 0, 0, 0. All of a sudden it makes contact, but the ball hasn't compressed at all yet. And so the force is really small. The more the ball compresses and flattens out, the bigger the force from the wall on it. And then the force gets less as it rebounds off. And then when it loses contact with it, the force goes to 0. I thought by embedding this in here, I used to have a link just to the YouTube, you know, so it would open up the browser, and then I had some problem with that and I embedded it in here, and I'm sure there's some sort of keyboard shortcut I can use, but I'm not randomly finding it here. So if we were to make just, you know, to motivate the notion of impulse, we're going to imagine drawing a graph of the force from the wall on the ball as a function of time. Let's imagine plus x is the direction the force is being pushed, right? So it's a positive force component in this case. It would be something roughly like this, right? It's 0 for a while. That's before the ball has touched it. And then it makes contact right here. The force is pretty small when the ball hasn't compressed much, but then it gets really big. There's maximum compression at that time, and then it starts decompressing. And when it's just about to leave, the force is almost 0, right? If it's only compressed by a couple of nanometers or something like that. There would be hardly any force. Okay, so from this, it's clear that the force from the wall changes the velocity of the ball. We're going to try to make this precise. How exactly does the shape of this graph, what properties of the shape of the graph influence how much the ball changes its velocity? It had a big change in velocity, right? It was going in that direction really fast, and then it was going in this direction really fast. So it had a huge effect on the change of its state of motion. And I want to ask, how might we alter the graph so the velocity change would be even greater than it is in this case? I know we don't have any numbers on here, but what could you do to the graph to make sure it had an even bigger change on the state of motion? In other words, the velocity of the ball between initial and final. What could I do to the graph? Yes, Sarah. Make it a shorter time interval, but so I guess just to be precise here, this is probably not what you meant. And I know the people at home can't see what I'm drawing right here, but suppose it was 0 all the way in here, and then it went up like that. That would be for a shorter time interval. Is that what you meant? Do you think that would have a bigger effect on changing the state of motion of the ball, or a smaller effect?
I guess I was thinking if time was shorter, then like the wall force would be bigger too.
Yeah, maybe. Yeah. So what I'm drawing here is not exactly what you meant, but one way would be to make it go up higher. That's essentially what you're saying. And we can make it go up higher by even keeping the force, the amount of time it's in contact, the same, but somehow make the force larger. So it seems like I'm exerting, this would definitely be true. If I exert the force for the same amount of time, but it's a bigger force on average, that seems like it would have a bigger effect on the state of motion of it. Another way to do it is just to have the force, in this case, the maximum force isn't any higher, but if I have that force act for a longer period of time, it seems like it's going to have more time to push it and keep changing its velocity from the state it was before to the later state, okay? So we're going to we'll see the ultimate importance of this later, because we're going to relate it to Newton's second law, but we're going to be interested in the notion of the area under the force versus time curve. For those of you who have taken calculus, the area under a curve sounds like a calculus concept, but we're going to turn it into a way where we don't need any calculus to do it. You could take, so for example, imagine this, curvy bell-shaped curve is actually the force that the wall is exerting on the baseball as a function of time. We could take the area that's under the curve and sort of smash it down and widen it out so that it has the same area, but I've formed it into a rectangle. And notice I've kept the width of the rectangle still to be from when contact begins to when contact ends. When we do that, the height of the rectangle that has the same area as the area under the original curve, the height by definition is what we call the average force that was exerted between the initial contact when contact ends. So if we want to calculate the area under the curve, if somebody tells us what the average force is, hey, that's easy. I just do the area under the curve is delta T times F average. I know how to calculate the area of a rectangle. So if we phrase it that way, it's easy to calculate the area under the curve. So sometimes we'll think of it that way, but there are a lot of cases where it really is a curvy curve, and you might need more information to know the area under the curve. So the area under the curve, the bigger the area under the curve, seems to be a bigger effect on the change in motion, the state of motion of the system. And so we're going to make a definition associated with that. We're going to call, so here I'm imagining that this force is only along the x direction and all the motion was just along x. We're going to call the x component of the impulse, we'll call that Jx. I don't know why J stands for impulse, but we're running out of symbols at some point, so J probably wasn't used. The definition of the x impulse delivered by a force, you have to say which force you're talking about, is the area under that force's for Fx versus time curve. Okay, and we can calculate that if we know what the average force is just by multiplying the height times the width. Okay. It's just a definition. We'll see why it's important in just a minute, but for right now, it's just a definition, area under the curve. Okay, let's look at the units, right? Impulse is defined as force times time. Force has SI units of newtons, time is seconds, so it has units of newton seconds. There's no shortcut unit for impulse. It's not as popular as watts. You know, people aren't calculating impulses on a day-to-day basis, so it didn't get a shortcut unit. If you unpack what newtons is in terms of more fundamental units, you could also find that it's Newton seconds is exactly the same thing as kilogram meters per second. And either one is an acceptable unit for impulse. Just got to keep an eye on time. Okay, now, so that's for a force being exerted along the x direction on an object. In general, a force that's being applied might have an x component and a y component and a z component. So we'd probably want to define the y component of the impulse is the y average force times delta t, and same thing for the z component of the impulse, right? Those are components of a vector that we call the impulse. Just like the velocity has an x, y, and z component, the impulse is a vector that has x, y, and z components. And it is defined as the average force vector times delta t. Okay, so there's an x, y, z component to that. So loosely speaking, that's a measure of how much a force has acted on an object over time, or the degree to which it's going to change the state of motion of the system. That's not a very precise statement, but now we want to say, let's use what we know about physics and find out exactly how does it change the state of motion of the system. And we're going to start with our friend that talks about this, how motion states changed. F net equals ma. F net equals ma is true at every instant in time. So we're looking at the acceleration, say, of the baseball and the net force being exerted on it. And, you know, above we were just imagining one force, the wall force, but there could be a bunch of forces, right? Since we're going to calculate the impulse using an average force, what we're going to do is average a force over a time interval delta t. So let's imagine at any time F equals ma, but let's average over a certain finite period of time. So F net average is equal to ma average. And our old friend, this was back from chapter 2, the average acceleration was defined as delta v over delta t before we went to the instantaneous acceleration, right? Why am I putting that in there? Because I'm going to multiply both sides by delta t, because I want to interpret this side as an impulse, right? And F average times delta t is an impulse. So let's multiply by delta t on both sides and cancel the delta t in the numerator and denominator over there. And what we get is m times delta v, or m times v final minus v initial. We're going to define now m times v as something called the momentum. So if an object with mass m is moving with velocity v, we call its momentum m times v, and it's a vector. It has, just like vx, v has an x, y, and z component, so momentum has an x, y, and z component. Okay, so we could just, this vector equation could be broken up into 3 equations about components. Okay, so finally, after all that, we're just a couple steps away from F net equals ma. This theorem that we're going to call the impulse momentum theorem, it says the net impulse delivered to an object, net means by all the forces that are acting on it, is equal to the change in momentum. So this is between some 2 times, right? We have an initial time and a final time. All these forces are exerted over a period of time. We find the net impulse delivered, which is the area under the net force versus time curve, x and y and z components. And that tells us about the change in momentum of the system. And notice the change in the momentum of the system is really telling us about the change in the velocity of the system. So that's what's telling us about the change in state of motion of the system, how much it's going to change. Okay, and again, that's just a different way of stating F net equals ma. We're supposed to do a worksheet now. I may just do this one together because we've got about 5 minutes left of our time, but I'm going to pass it out. We have other problems on here, so please bring this worksheet on Monday. Yes. Yeah, the change in momentum is sort of related to the change in velocity, right? It's just mass times change in velocity. So we're focusing on an object and we're interested in how much its velocity changes, or the mass times the velocity is the momentum. And what is determining that on the left-hand side is something about how all the forces that are being applied to that object act over time. So again, we've got to be careful to define what is our object, and then think about all the forces that are being exerted on that object. Each force that's being exerted on the object is going to have an associated impulse, and the net impulse is just the sum of all those impulses. Now, when I say those words, you're not used to thinking about impulse, I bet, and so they just sort of evaporate away. We're going to need some practice with this to kind of figure out what's going on. Okay, so let's just look at this as our last problem of the day. Problem 1, 5 kilogram hockey puck is initially traveling on frictionless ice, so it's moving horizontally, and we're given some initial velocity components, -3 and -1 at time t equals 0. And a force is applied for a certain amount of time. Now, if you thought about this problem carefully, you could do it using kinematics. We would find out if the force is constant, the acceleration is constant, we have the initial velocity, we could probably figure out what the final velocity is. But look, I'm just going to encourage us to use the impulse momentum theorem here to try to figure out what the final velocity components are, right? So here they are right here. I'm just going to write down the impulse momentum theorem. The shorthand form is the one that's on the top version in the lower left box, and the expanded one is in the bottom there. Let me unshare the screen and click on there so I can still see it. So we know something about the ice. We're looking down from the sky, right? This is the ice here. So if we have X and Y components, Y is not up, right? Y is horizontal. X is also horizontal. We're staring down from the sky in this view, right? And let's write down the impulse momentum theorem. The impulse momentum theorem says that the average force, X component, and we need to take the net, that means add them all up, but in this case, there's only one force that's acting along the X direction, right? There certainly is a normal force and a gravitational force, but neither of those have X components, so I don't need to worry about when I'm doing the X component of the impulse momentum theorem, I don't need to worry about it. Net force average times delta T, that's the X net impulse that's being applied to it, is equal to the change in momentum, m times Vx final minus Vx initial. Let's see if we can plug things in there. Again, there is a weight force. It has 0 X component. There is a normal force coming out of the board on whatever's sliding. A puck? Yeah, hockey puck. But it has 0 X component. The only other force is the force that's pushing it in the plane, and we're told the X and Y components of it. So if we're doing X components here, this would be a 2 Newton force, right? And the amount of time it acts for is 4 seconds, if you read the text carefully, all right? So this would be an impulse X component of 8 Newton seconds. That's one of the allowed units for impulse. And that would be equal to the mass of the object, 5 kilograms. I don't know, I'm not a hockey player. I made that up. It's probably way too massive for a hockey puck. I bet they're less than 1 kilogram. That sounds ridiculous, but okay, take it at face value. Closer to a curling stone maybe, or something like that. All right, times Vx final, that's what we want to solve for, one of the two things we want to solve for, minus Vx initial. So Vx initial is minus 3 meters per second. Got to keep those minus signs in there. And we're going to do the same thing for y components, right? Let me just write the y components down here without writing the y equation above it. The y force component is minus 3. It's being applied for 4 seconds also. And that same mass here, Vy final minus Vy initial was minus 1. Okay, and I can solve for Vx final and Vy final. It's not so exciting. They're both negative at the end. Vx final is equal to minus 1.4 meters per second. Vy final is equal to minus 3.4 meters per second. I'm having deja vu that I can't remember if I've corrected it, but I have, maybe someone can check these numbers because I'm having deja vu that this was something where I had made a calculation error before on this worksheet. If you're getting something different, it's probably not you, but I think I may have corrected it at some point after 2 years of people telling me that they disagreed. In any case, you know, the same thing we could have gotten from F net equals ma or kinematics kind of stuff. Here we're getting from the impulse momentum theorem. So it doesn't seem so exciting, but we're going to see other ways in which it makes our life easier on Monday. All right. Have a great weekend.